Today we continue our lectures with more practical devices. So before, in the first three lectures, we looked at the constraints and the requirements of our wired and wireless communications. Now we have to look at the components we're going to build these devices, receivers, transmitters, and other equipment used in wired and wireless communications. And the first thing to do probably is we have to repeat what kind of semiconductor devices we have available, because if we do not have these semiconductor devices, it's very little we can do. We can build filters and some passive components without semiconductors, but when we need processing, when we need non-linear processing, when we need amplifications, then semiconductors is the only choice we have. And in fact, the technology of radio starts with semiconductors. In the first part on semiconductors, so this week we are going to look at diodes with semiconductors that have two terminals. The next lecture next week will be on transistors, so devices that can amplify signal in a much easier way than other components can do. There are diodes that can amplify signals that have negative resistance, but the practical way today is to use transistors for that purpose. So today for diodes, to study the nonlinear behavior of diodes in different regimes of operation, different kinds of diodes, to see what we can do with diodes. And in fact, radio technology starts with diodes already more than 100 years ago, with the use of crystals as rectifiers, as radio detectors for very high frequencies, where other technologies failed or were very insensitive. So the first radio receivers, actually Heinrich Hertz, used a spark gap receiver that required at least 100 volts to trigger. Then that was replaced by some more sensitive receivers like magnetic receivers used by Marconi that worked perhaps with 10 volts voltage, RF voltage, radio frequency voltage. Then vacuum tubes came around, vacuum diode that could work with 1 volt voltage, and finally the best solution was to use crystals, nonlinear affecting crystals that may give useful performance with 100 millivolts of signal. So 1000 times less than a spark gap, 1000 times less voltage, so that means 1,000,000 times less power required for such a crystal to work. So what was the first radio receivers? The first radio receivers they had a band pass filter on the antenna. Also the antenna worked as a part of the band pass filter, and a rectifier that converted RF signals into audible low frequency signals in an earphone. So this was the simplest requirement for this receiver. So the antenna was usually connected to a tune circuit, an inductor and a capacitor, a variable capacitor to adjust the frequency of this device, maybe also a variable inductor with an adjustable tap to match the impedance of the antenna, and a crystal. One of the most useful crystals 100 years ago, one of the most useful crystals was the lead sulfide. Lead sulfide crystal, or galenite crystal, is a lead ore. It's found in nature, and selecting the with the sharp point, the proper operating point, it shows rectification effects. So the current flows in a different way in different directions. So in this way, the current flows easily, while in the opposite way, the current flow finds much more resistance. Unfortunately, the lead sulfide crystal was really very good at this work, but it was also tricky to work with it, so it could be easily damaged with over voltages, say from a lightning collected by the antenna. It could be easily damaged mechanically. It's not mechanically very stable, so it was not a very good diode, but it had some interesting properties, so it could work with very, very low voltages, both on the RF side and then the audio frequency side, getting to the earphone. So this was 100 years ago, and the first radio sets used, okay, a high power transmitter was used in the long wave and medium wave regions, and very simple receiver sets including just a tuned circuit, a crystal, and an earpiece. So talking about 100 years ago, in fact, this lead sulfide crystals was one of many semiconductors. Here I listed many of the semiconductors we are using today, but these many semiconductors, we should understand that the world is not just made of silicon. Silicon is perhaps the most important semiconductor, but there are many other semiconductors that have different properties, and sometimes we cannot go without them. So lead sulfide was interesting because it had a very low band gap. The energy band gap between the valence band and the conduction band of a semiconductor is a measure how our material is going to perform. If the valence and conduction bands overlap, then we have a perfect conductor like a metal. The wider the band gap, the better the insulator the material is. So silicon oxide, which is a very good insulator, has a band gap of 9 electron volts. Semiconductors mainly have band gaps within half a volt at room temperature, talking at room temperature, and perhaps up to 3 volts for gallium nitride semiconductors that have some useful performance at room temperature. At cryogenic temperatures, other compounds may be useful that have a much lower band gap, useful to detect infrared radiation. And at very high frequencies, at very high temperatures, semiconductors like diamond is also a semiconductor, but a pretty wide band gap. It's at room temperature, it's quite a good insulator. Transistors can be built out of diamond, but operating at much higher temperature than the room temperature. So this is the constraint we have on the other end. Silicon with the band gap of slightly more than 1 electron volt is almost by definition our semiconductor of today. There are other semiconductors that we would prefer we would not have them, like copper oxide. Copper oxide, we're not going to use it today. Many years ago, some rectifiers, low voltage rectifiers, were built from copper oxide. But copper oxide today is a nuisance. It's a nuisance because copper oxide grows on our antennas. Since it has rectification properties, fortunately it's not a very good rectifier. It causes distortion to our signals, and it causes intermodulation distortion, so it causes interference in radio communication. So copper oxide is a problem, but it's still a semiconductor. There's the problem. Some semiconductors were used in the past, like selenium. Selenium rectifiers were used in the past for mains frequency 50 Hz or 60 Hz rectifiers, but they are very slow. They have very low electron and hole mobilities, so not very fast. Only very slow diodes can be made out of selenium. Some compounds like lead selenide, lead telluride were used as photodetectors. Yes, talking about photodetectors, we used also other compounds like cadmium sulfide, cadmium selenide, cadmium telluride. This was all used to build photoresistors. An important family of semiconductors is a 3-5 family. One component of the third column in the periodic table and one component from the fifth column, like gallium arsenide, gallium phosphide, gallium nitride, and other 3-5 components. Why are these 3-5 components important? First, they are useful as detectors, since we can make different width band gaps. So wider band gaps, both wider band gaps and narrow band gaps as silicon, and that's important for building photodetectors, even if we may have to cool them at very low temperatures. On the other side, silicon is a very inefficient generator of light. 0.01% is the efficiency of silicon LED if we built a light emitting diode out of silicon. Because silicon is an indirect indirect bandgap semiconductor, the likelihood to generate a phonon, a particle of thermal movement of the crystal lattice of silicon, is much more likely than creating a photon, a particle of light. On the other hand, the generation of photons is very efficient in gallium arsenide, in gallium nitride, and other 3-5 components we have here. So we need these components. Finally, we may play tricks by making alloys of different semiconductors together, like silicon germanium. This is very important today to build transistors, very efficient transistors for very high frequencies, like indium gallium arsenide that's used for photodiodes. So changing the mix of indium and gallium, here changing the ratio of indium versus gallium, we can adjust the band gap exactly to the value we need in a photodiode. Or in a light emitting diode, it's the same story, or laser, semiconductor laser. Finally, if we need photodiodes for very long wavelengths, like thermal radiation, 10 micrometers, then mercury cadmium telluride is a semiconductor of choice. Of course, this mercury cadmium telluride, if we want to make it useful in the very long thermal wave infrared region, we have to cool this detector down to cryogenic temperatures. With detectors, similarly to the band gap, also the dielectric strands of an intrinsic, so not doped material, follows mainly the band gap of the semiconductor. So usually materials with a low band gap have a poor dielectric strand. Materials with a wide band gap, like gallium nitride, have a very high dielectric strand. Yet another fact when we build our devices, and especially transistors, so this will be next time more important, is to check the electron mobility and hole mobility. Both electron mobility and hole mobility define the speed at which a semiconductor device may work. But if the electron mobility is higher, we'll prefer to use electrons in our device. If the hole mobility is higher, we'll prefer to use holes in our device. You see that for silicon, electrons are about 3 times faster than holes, and in fact, N-channel transistors, most transistors, are 3 times faster than P-channel transistors. Well, but with silicon, this difference between mobility of electrons and holes is not as large as it is in 3-5 semiconductors. In 3-5 semiconductors, like gallium nitride, which can be used for very high frequency, very high power transistors, electron mobility is okay, but hole mobility is very low. So we are not going to make p-channel. It does not make sense to make p-channel transistors out of gallium nitride. The same for other semiconductors. Also, gallium arsenide electrons are much faster than holes, and also indium phosphide, another important material to build very high frequency devices. Electron mobility is much higher than hole mobility. Please don't take these numbers. I took these numbers from several sources, and on the same material, usually many different sources disagree on the values of electron mobility and hole mobility, depending on the way these parameters were measured. So I tried to compile this table out of average values I could find in the literature, but the literature on many occasions disagrees by at least a few percent on the measured values of electron mobility and hole mobility. The same about the electric strand, they also disagree. The only thing we can measure accurately is the band gap of the semiconductor. So with a semiconductor, we are going to build the simplest component we can build are diodes. So in other words, rectifiers. Devices that behave in a different way for current flowing in one direction than in the other direction. And of course, we want to make it as much different as possible. For a rectifying junction between two different materials here, we have the diode equation. The diode equation where we have the forward the voltage applied to the diode, this is U here, the current through the diode, this is a physical constant, saturation current, depending on our diode, charge of the electron, Boltzmann constant, absolute temperature, and this N is the ideality factor of a diode, so the way minority carriers are getting recombined in a rectifier. This ratio here, charge of an electron divided by Boltzmann constant divided by temperature, this ratio is has the units of volts, and in fact at room temperature it's around 25 millivolts. So we are going to call this thermal voltage to simplify our equations, not to carry around so many physical constants here. This is for the ideal diode without other effect, just the diode effect. And we see that for different semiconductors, we can build a rectifier with as a p-n junction. A p-n junction joining, so doping a crystal of silicon partly p with and partly n. So here we have an excess of electrons. Here the majority of carriers are holes. In between we have a thermoelectric contact voltage that builds this depletion region when where charge carriers are depleted. This is actually an insulator because holes moved in the p region and electrons moved in the n region. This depletion region forms each time we connect together different materials. How do we connect then, how to make an ohmic contact to a semiconducting material? Well, without creating a depleted region, carefully selecting the metal here, but also heavily doping the semiconductor. If the semiconductor in this region is heavily doped, or here is heavily doped, or here is heavily doped, then this IS is very, very large, and this is practically an ohmic contact. This curve moves down to zero here. So what is the behavior of our p-n junctions if made from silicon, many years ago for germanium, for optoelectronic devices from 3-5 semiconductors? Well, the band gap differs, and also IS also differs in a very wide range here. This is quite handling this IS is quite tricky because handling such low values is very difficult here. So it's much more common to use the voltage at which the current through the rectifying junctions in the forward direction reaches 1 milliampere. 1 milliampere, this U 1 milliampere is the voltage across the diode when biased in the forward direction, and when the current achieves 1 milliampere. This is a much easier figure to work with different semiconductors. We have different figures here, and this U1 milliamp, okay, it does not depend only on the semiconductor. It depends on the doping on the semiconductor, and it also depends on the area of the diode. What is the area here of the diode? So usually it's about 0.4 volts less than the band gap energy written in electron volts. So this is a practical equation. It's not exactly true for all semiconductors, but it's close. It's close. So it differs for different junctions. So these 5 diodes here, all 3 LEDs and p-n junction of silicon and germanium, all these are p-n junctions. LEDs also contain p-n junctions. While Schottky junctions are junctions of semiconductor to the appropriate metal. And Schottky junctions have an even lower voltage drop than the band gap. It still follows the band gap. So the wider the band gap, the larger the U1 milliamp, but this voltage is far lower than the voltage on the p-n junction. So Schottky junctions will behave in a different way. How do these curves look like? So here on this plot we have voltage on the horizontal axis, current on the vertical axis, and we do not have any action only here in the forward region. In the forward bias region, this means that we have forward bias we put on the anode. This is metal in a Schottky diode or P semiconductor in a PN junction. It's positive and the N is negative. The N doped region is negative. This means forward. This is actually forward bias. So plus to the anode and minus to the cathode of our diode. This means forward. Of course, diodes may have a behavior, some behavior also with the reverse bias, with the polarity of the power supply reversed. So if we plot here things, we see that in the forward region we have the standard behavior of a silicon PN junction plotted here in red. Of course, light emitting diodes have a much larger voltage drop than silicon diodes. So this U1 milliamp is much larger. While Schottky junctions, still made from silicon, have a much smaller voltage drop, and we may make use out of this. We didn't say anything about reverse bias. Of course, talking about reverse bias, there is certainly a voltage when our rectifying junction is going to break down, no matter whether it is a Schottky junction or a PN junction. These breakdowns differ according to the amount of doping of impurities in our semiconductors. So in order to see a large breakdown, voltage breakdown, we have to have very light doping here, very clean semiconductors we have to use. On the other hand, if we have highly doped semiconductors, like in a tunnel diode, this is actually a germanium tunnel diode, the curve. A germanium tunnel diode has this peak, spurious peak here as 0.1 volts, and at 0.4 volts it has a value. So even though it's made of germanium, this would be, the green one would be the curve of a normal germanium PN diode. So there are other effects like the tunnel effect. The tunnel effect is frequently used in Zener diodes. Zener effect or tunnel effect is the same. And it's used for stabilization, voltage reference diodes up to -7 volts. So at -2 volts, the tunnel effect has a pretty smooth curve here. There is no knee observable here. So these are not really very good Zener diodes, very good voltage stabilizers here. While above -7 volts, this is for silicon, above -7 volts, we have avalanche breakdown in silicon. Avalanche breakdown is not destructive in silicon, so we can use diodes in this regime, like making a stabilizer diode for -12 volts here. We should also consider that in silicon, both effects have a different sign of the temperature coefficient. So the temperature coefficient in silicon cancels out at the breakdown voltage of about -7 volts. This is also a tunnel diode, and further increasing the doping, we get the real tunnel diode that has a very high conductivity already at 0 volts bias. Curve in between this one and this one, but I cannot draw everything here, is the so-called back diode. The back diode has this big drop down, but still it has better conductivity, higher conductivity in the reverse bias rather than in the forward bias. And the back diode is also a kind of tunnel diode, not used as a negative resistor like the true tunnel diode, but used as a high frequency detector, because the tunnel diode is usually operated in the tunnel region. In the tunnel region, we only have majority carriers. We do not have the charge storage of minority carriers that slows down PN junctions in the forward region. Under the forward bias, silicon has a very well-known thermal coefficient of about -2.2 millivolts per degree Kelvin. And we should consider this while designing our circuits, because this figure, especially with transistors, can lead to thermal runaway. So this is actually a dangerous effect. The voltage drop across the diode is decreasing as the temperature is increasing. The plot is of course not to scale here. So let's look now at the diode symbol and diode packages. We always refer to the N-doped side as the cathode of the diode, and the p-doped side or metal as the anode of the cathode. Depending on the application of the diode, these diodes are not necessarily different. Say a rectifier diode may also act as a Zener diode, may also act as a varactor diode. So they do not really indicate the kind of doping here. But some devices are like a Schottky diode has a metal anode. That's the difference. But it's still, the cathode is marked. The cathode, the semiconductor side, is marked on its package. On its package, always cathode has a ring or a dot or some kind with the shape of a package, or a plus sign, because as a rectifier they provide a plus sign, or cutaway on LED packages, or a ring on SMD diodes. So this is always the cathode is marked on the diode. There are special diodes, like varactor diode is nothing special. We just want to stress with this capacitor here that this diode was actually designed to work as a varactor diode. But Zener diodes, which are also p-n junction diodes and conventional rectifier diodes, also make good varactor diodes, so it's not really something different. There are some components that are a little bit special, like back diode or tunnel diode. These two actually have a better conductivity in the reverse, under the reverse bias rather than the forward bias. So that's the reason for this symbol, but they are still p-n junction diodes. What does not have a p-n junction is a GaN element. The GaN element has no rectifying junctions. We will see later on how it operates. And there are some more complicated two-terminal devices like a diac, but the diac has at least two rectifying junctions. We are not going to deal with the diac because it's not frequently used in communications. What we do have special diodes is if we use our conventional diode as a photodetector. So if we if we are making use of the photo effect in the diode, of course, if we specially design the diode to be very sensitive to light, we call it a photodiode. This here usually the design is a little bit different than this one here, but also a standard rectifier may work as a photodiode, though not very efficient. Diodes made of some material may also emit light, like light emitting diodes or laser diodes, but here silicon is a bad choice because it has an indirect bandgap. Here we should use a 3-5 semiconductor that has a direct bandgap that does not require a phonon to be generated, but all the most of the energy that's released with a recombination of an electron and a hole is released as photons, so as light. So here silicon is not a good candidate. But even today LEDs and lasers, we use them in most of our communications, especially over optical fiber. If we go now to see different kinds of diodes, I would first prefer to start with the reverse bias, because I already talked here about the reverse bias. So reverse biased avalanche breakdown, avalanche diodes or Zener diodes are good voltage stabilizers. So what they are good for. This is not rectification really. Rectification would prefer to have the curve hole here and the curve here like this. p-n junction. A rectifier is the simplest application of a diode. So now the idea is to use this depletion region here. This depletion region is without bias, it is not conductive. In a p-n junction, both p and n rather lightly doped. If they were strongly doped, we would get a tunnel diode. And this actually makes a capacitor. If we apply a reverse bias on this diode, we can make this depleted region larger, and thus with the same area we have a larger spacing between the electrodes of this capacitor. We reduce the capacitance, so we can make a tuning diodes. That's usually called a varactor. Here what we would like to have with the get from the varactor, we would like to get the highest possible capacitance ratio between the say maximum capacitance C1 and minimum capacitance C2. Maximum C1 is low voltage, minimum C2 is close already here to the breakdown. Okay, this effect happens with all diodes, but this exponent gamma depends on how diodes are doped. If we have a linear doping profile from P to N on a PN junction, this is not particularly useful. It's useless even for conventional diodes. This is not a good diode at all. And it has a very small ratio C1 to C2. We get a much better ratio on an abrupt junction, so an abrupt transition from P to N. And this is what, say, Zener diodes are built, or avalanche breakdown diodes. So this is already used in many semiconductor diodes that are manufactured. But if we want to have the maximum ratio here from C1 to C2, we specially tailor the profile of the doping. We specially tailor, so we have an N sections here, decreasing, first the doping decreasing, and then finally increasing on the contact side. What would we get with this side? With this we will get a very high ratio of capacitances here. So a very high tuning ratio here. So hyperabrupt doping is actually what is interesting for us. We should also understand that varactors have a limited Q because of the limited conductance or resistance of these contacts in any such diode design. And in order to get the best, so I think here should be G times oh, it's okay. So we should understand that how to build our diodes. First, we should understand that in silicon, the mobility of electrons is much higher than the mobility of holes. So we would prefer to build our depletion region in the N section, because this N section has a high resistance, and with N doping, the resistance, because of the higher hole mobility, is much smaller than with holes. So with N, with the depletion region extending into the N doped region, we get a better Q than with the P region. So P is usually we usually design the diode in such a way that we have no depletion in the P region. So this is really useful here. This is damaging. This is destroying the performance of our diode. But we will grow our depletion region into the N, so we dope less N to have the same charge at a much larger distance. And finally, we can also select better semiconductors. So the mobility of electrons in gallium arsenide is almost 4 times the mobility of electrons in silicon. So we can make a much higher Q of our diodes using using gallium arsenide in place of silicon. Of course, in gallium arsenide only electrons, only N-type material. P-type, the P-type material, the mobility of holes in gallium arsenide is very low, so it would be very, very damaging to the properties of our diode. If we look at here at up, so we have silicon, mobilities in silicon. We are looking for the highest values, not this one, but this one in gallium arsenide. This 5000 is a better solution. Sorry for the units. This is what semiconductor people are using. Still centimeters, not meters, but they are used to these figures because of history, for historical reasons here. So we are trying to make a hyperabrupt junction like this one here, with the gamma larger, this exponent larger than 0.45 to have the highest possible capacitance ratio. And let's see how this diode work in the next picture. In the next picture we have now here, this is not, of course it's not plotted to scale this. We have a highly doped P region and quite demanding doping of the N region here. The depletion region at low voltages extends mainly in this slightly higher doped N region here, in the darker blue here. as we increase the voltage, the reverse voltage, the depletion region extends into both semiconductors, in the P semiconductor and in the N semiconductor. But now, as we get in the lighter doped NFX region here, so this is more heavily doped, medium doped, very light doped. Here we have very little charges. So for slightly larger bias voltage, this thing now here it was moving slowly because of the high amount of charges in this region, but here it is moving very quickly because of the low amount of charges we have here in this region here of the doping. Of course, even varactor diodes reach their breakdown when this region extends to the N plus substrate. This is the substrate of the diode. When this region, the diode is usually designed to get to the avalanche breakdown in the diode. This is not usually not a problem in silicon, but could damage gallium arsenide diodes. In this way, we have a very slow movement here, very narrow depleted region here for very high capacitance, very wide depleted region for very low capacitance. So with this special profile of doping, we get because of this high end doping here, we had a very narrow region here. Because of this low doping here, we had a very broad region here. A large ratio of the thickness of this capacitor here means a very large change of the capacitance here. So this is the trick how the hyperabrupt doping profile works with varactors. Well, abrupt we can get, we need not even buy a varactor diode, we could use a Zener diode here. It's equally good here. One final comment about the diodes. All this region here has quite a high resistance. So Hyperabrupt-varactor has quite a large resistance, series resistance at low reverse bias. This series resistance drops only at high reverse bias. So the Q of this varactor here may be quite low because of this high resistance here or low conductivity. So the Q of a hyperabrupt-varactor is a very complicated function of the applied reverse voltage here. So this is perhaps the simplest way to use PN junctions. One of the use we are starting with reverse bias. We started reverse bias with the avalanche breakdown here. Now we went down to the capacitive effect, so variable capacitor, and we can use these variable capacitors to tune our LC circuits. In place of a mechanical variable capacitors, we could use one varactor and feed this varactor with a bias voltage through this high resistance here. This resistor may be mega ohms because there is almost no current drain to the varactor. We apply a DC bias voltage to adjust the capacitance of this varactor, and this C bias here is just used to decouple DC and couple RF, so we have almost the whole capacitance of this diode across our coil here, our inductor in our tuned circuit to tune the circuit. What is a problem with this circuit here is that this capacitor is actually non-linear, so the depletion region does not change only with the DC applied reverse voltage, but also with the RF voltage, and this makes a non-linear capacitor, and this non-linear capacitor may cause distortion, may cause harmonics in our circuits. Okay, there are varactors especially designed to produce harmonics of the signal. So this is another application of varactors to produce harmonic. But if we don't want harmonics, then a very good trick is to connect two varactors in series, and this is actually anti-series. Anti-series, so that we apply the same bias, DC bias, to both varactors, and we apply the RF voltage to one varactor with the reverse polarity of the other varactor. In this way, if one varactor increases its capacitance, the other varactor decreases its capacitance. And in this way, this delta C actually cancels out. It does not cancel out completely, but it cancels out to a huge extent. So this is a much better solution if we don't want distortion we had here. Much better solution is to use two varactors, and in fact, if we look at this formula in detail, just about half of the RF voltage is applied to each varactor. Just half of the RF voltage if the capacities of the varactors are about the same. So with half the voltage, we have half the effect plus the cancellation of the effect, because when one varactor increases its capacitance, the other varactor decreases its capacitance. So this is the usual way to make varactor tuning. This is very frequently done using two varactors in anti-series connection. So this is about varactor tuning. Of course, we should care about the Q, and the Q may be quite low for silicon varactors. This Q at 1 gigahertz, it's just about 30, or about 10 at 3 gigahertz. So the Q may be very low at microwave frequencies for silicon varactors. Of course, it's 4 times better for gallium arsenide, because gallium arsenide, for the same charge on the plates, for the same charge in the depleted region, has 4 times the conductivity, so 4 times higher Q, so 4 times the G for the same C junction. This is about tuning varactors. Of course, the other thing to care about is here to have a high impedance bias resistor here, not to load the RF circuit with this bias resistor, or an RF choke, but resistors are preferred to chokes, because chokes introduce additional unwanted resonances of our tuned circuit. So we have to be very careful what kind of bias device we put here. Okay. Then the next thing, we have to look at the diode under the forward bias when the diode equation applies. We have the diode equation under the forward bias. How does this diode behave dynamically in our circuits? And the first thing we observe with the diode, this diode has a differential resistance. The higher the current through the diode, the lower the differential resistance if we go along the curve. If we look at this curve here, the higher the current, the steeper the curve, the lower its differential resistance, the steeper the tangent to this curve here. We can calculate this, and under forward bias we assume that the diode equation holds. It does not hold under the reverse bias. Under reverse bias here the diode equation does not hold, but under forward bias we are pretty accurate with this equation. And in order to get the differential conductance, we can simply differentiate current versus voltage. We can calculate this differentiation, and if we look at the result here, this result here, actually this is the current through the diode. So we have the differential conductance expressed with the current. If we flip the result, we have the differential resistance expressed with the current, expressed with the thermal voltage, expressed with the diode ideality factor. So we can pretty assume that for an average diodes, n will be silicon diodes, n will be between 1 and 2. So I took here a value that n times ut is around 40 millivolts. This is slightly higher than 1.5, but this is okay for rectifier diodes. At the current 1 milliamp, the differential resistance will be 40 ohms. So 40 millivolts divided by 1 milliamp is 40 ohms. So we know what the differential resistance of our diode is. This is for DC, the DC behavior. But we yet have another effect. With diodes, and diodes under the forward bias, when the diode equation holds under the forward bias, diodes actually we have lots of electrons going from the cathode to the anode, and in the anode, inside the anode region, they are minority carriers in the p-doped region, and they have to recombine before they transform from conductive current of electrons, from convection currents of electron into conductive currents of holes. The opposite is at the cathode. Here, holes coming from the anode become minority carriers. They form here a convection current of holes, and this current will only transform into conductive currents of electrons in the n-doped cathode after some time. And this time is the recombination time of in other words, the minority carrier lifetime. In this way, quite a large charge is stored both in the anode and in the cathode, because this minority carrier lifetime may be quite large. So if we what this stored charge makes, when we have a forward current through our diode, we get lots of charge. Lots of charge means additional capacitance here. So this is C of minority carriers. This is, of course, the amount of charge differentiated by the change of voltage. And if we look at our equations, this is just the minority carrier lifetime times current differentiated per voltage. And we already calculated this. This was the differential conductance of our diode was here. So differential conductance multiplied here by the minority carrier lifetime, we get here the capacitance. And this capacitance, considering the figures of conventional diodes, may be quite large. Okay, so the admittance of our diodes becomes the differential admittance here of our epsilon delta here becomes y delta becomes the real part. The real part is the differential conductance, and the imaginary part is j omega times the sum of all conductances. And all conductances, we have some conductance of the junction capacitance we had here in the varactor, the junction capacitance here, but a much larger capacitance than the junction capacitance is this capacitance of the minority carrier, and this may become very large. If we look at an example here of typical diodes we have, I used here very common semiconductors we are using in our circuits, like a rectifier diode, a low frequency rectifier diode, high voltage rectifier diode with a PN junction, that's 1N4007, a small signal diode, fast diode, a PN junction with gold doping, and a diode that was specially made for RF switching with the lowest possible capacitance. As a pin structure, this diode is specially made for switches in the few gigahertz region, say from 1 gigahertz to 3 gigahertz about. So that's the reason for its low junction capacitance. These junction capacitances are at zero bias or slightly negative bias. But the most important parameter now to understand here is the minority carrier lifetime. This minority carrier lifetime in silicon may be quite large. For the rectifier diodes, where we need we want high breakdown voltages, we use very clean silicon. Very clean silicons, this minority carrier lifetime may be very large before electrons and holes recombine with the opposite charges in the minority carriers recombine with their opposite charges in the host semiconductor. And this may be in the order of 10 microseconds. It's not infrequent even to see 100 microseconds here. This is pretty slow for electronics. And you see here that at 1 milliampere, while the diode has always 40 ohms. All three diodes are silicon diodes. All have 40 ohms. Perhaps this one has a slightly smaller resistance because the ideality factor here is lower for this one and for 147. So this would be perhaps more appropriate to take 30 ohms here, not 40 ohms, and a slightly lower capacitance. But I didn't want to mess here, just to make things simple. So this 10 microseconds at just 1 milliampere current makes a huge capacitors. 250 nanofarads is almost 4 orders of magnitude, so 10,000 times larger as a junction capacitance. So the slow rectifier diodes has a huge minority carrier capacitance. And this is the reason why this diode cannot be used in switching power supplies operating at a few, even at a few 10 kilohertz frequency. At those frequencies, this diode is already short circuit. It's no longer a rectifier. This is only a rectifier for 50 hertz. At 100 megahertz, the differential impedance of this diode is, of course, it's because of this very huge capacitance of minority carriers. The impedance is very, very low. It's milliohms. So this is practically a closed switch here. The microwave switching diode, the bar 81, has a carrier lifetime much lower. It's around 100 nanoseconds. 2.100 nanofarads, but even that is not far away from a short circuit at 100 megahertz if we think that RF circuits operate with a characteristic impedance of 50 ohms. And this impedance is even less at the higher the frequency. So I said before, bar 81 was designed for the frequency range between 1 gigahertz and 3 gigahertz. So it's already 10 times lower, this value, at the higher the frequency. What makes fast diodes out of silicon? Still, we have a PN junction in the 1N41, right? This is a very well-known small signal diode, silicon diode. But besides the PN junction, it also has gold doping of the silicon. Gold doping reduces the minority carrier lifetime. It reduces the minority carrier lifetime just to 5 picoseconds. So this diode here will have 125 picofarads of minority carriers plus 4 picofarads of junction capacitance and 5 nanoseconds minority carrier lifetime. This is much shorter, 3 orders of magnitude shorter than the rectifier diodes, more than 3 orders. And its impedance at 100 megahertz is already several ohms, and we could not neglect here the real part. This is the real part here, but this is the real part in the admittance. Now we have to invert this, and while inverting this, 40 ohms becomes 40 ohms parallel equivalent becomes 3.5 ohms series equivalent. And here 12 ohms parallel equivalent, J12 ohms parallel equivalent becomes J11 ohms series equivalent for the impedance. What we should know also, besides all this discussion, is that Schottky diodes are really fast. In Schottky diodes, we do not have minority carriers, nor we usually do not use minority carriers in back diodes, though we can make them if we want in a back diode. But in Schottky diodes, we have no minority carriers at all, because we don't have because electrons travel from silicon through the in the Schottky diode, electrons travel from silicon through the depletion region directly into the metal. So there is no accumulated charge of electrons in the metal, and there is no holes coming from the electron into the N semiconductor. So there is no tau. This tau is equal to 0, and Schottky diodes are really fast. And that's the reason why, well, if we are working with high frequencies, we'd prefer to use Schottky diodes, because Schottky diodes do not exhibit this effect. They are still behave as varactors, so still Cj is an important parameter, junction capacitance of Schottky diodes. We could use them as varactors, but not as the much larger capacitance of minority carriers in Schottky diodes is inexistent. So this is enough for this hour. In next hour we shall see how to make good use of Schottky diodes, how to design Schottky diodes, how to make good use of Schottky diodes in the real world. And of course proceed with other types of diodes.